Hey guys, welcome back to a new video. In this session, we'll be solving exercises step by step on hydrostatics, which is a field in physics that studies fluids at rest, and fluids can be either liquids or gases. It will be the first video in the series on the broader field of hydrodynamics, which studies fluids in motion. In this first video in particular, we'll be looking at the concepts of pressure and the force that comes with it. First, we'll be doing some conceptual questions to get a more intuitive feeling of the behavior of fluids at rest. Then we'll be solving more traditional physics problems where you have to do some calculations in order to get a result. The timestamp for each of these exercises can be found in the comment section below. And as always, if you have any questions along the way, feel free to ask them in the comments down below or join our community by visiting the Discord server where you can freely interact with fellow students and myself. Also, if you enjoy these videos and you learned something, consider giving them a thumbs up, which helps out getting them in front of more people. And with that said, let's get into the first exercise. First, let's go to the conceptual questions, just to get a better understanding of how fluids behave when they are at rest. Let's say that we have a container, which is watertight, which we are going to fill with water. Now this container has three peculiar openings. One very small opening, a tube-like opening, one which is very broad at the top and very small at the bottom, and then the third one which is the exact opposite, which has a very small top but a very broad bottom. Evidently, when we slowly start filling this container with water, the water level will rise, and at some point the water level will reach the bottom of our three openings. If we then keep filling the tank with water, the water level will rise in each of these three openings. And it's on the basis of the shape of these three openings that we'll be considering some basic questions. The first question that you might ask is, how will they fill up? Meaning, how does the rising water level in each of these three openings compare to one another? Now you might be inclined to think that it will rise faster in opening A, because opening A is much smaller and therefore needs much less volume in order to fill up, and therefore it needs much less water for the level to rise. This means that while filling the tank slowly with water, at a specific point the water level in A will be larger than the water level in B and C. However, this runs into a problem. Because these openings are basically connected with the same water source or the same tank, they can be seen as the same container. And therefore the surface or the interface between the water and the atmosphere outside in each of these openings can actually be seen as the same surface. Now, because we know that in any container, the surface of the water will always be level. This means, in this case, since we can consider all of these three openings as being from the same container, the water level in each opening will be the same, and it will be so at any point during the filling of the tank. The important point here is that water surfaces that are connected to the same container will always be at the same level. So to answer our initial question, how will they fill up? Well, basically they will fill up at the same rate, meaning that the height of the water level will change at the same rate and at each point will be exactly the same. And the underlying principle here is that communicating weights will always have the same height of water surface. Let's now go to the second question, which is in the scenario where we stop filling the tank with water, meaning that it will be a static fluid at this point, and where the height of the surface will be the same in all of the openings. Now in this scenario, we will ask ourselves the question, what is the pressure in the fluid at its surface? So at an infinitesimal distance below the surface of the water, or said differently, the interface between the air and the water. To make this clear, let's draw the surface of the water in large at any of the openings, where this would be the water and this would be the air. We know that in the air, for example here right above the surface, the pressure will be equal to 1 atmosphere. And what exactly this means, we will see in the next exercise, but basically it's just the pressure that we experience on the surface of the Earth due to the atmosphere pushing down on us. And now the question is, what would be the pressure right below the surface of the water? And it turns out that at this specific point in the water, right below the surface, The pressure is also 1 atmosphere, so equal to the pressure right above the surface of the water. And to see why this is the case exactly, let's see what would happen if this were not the case. And for this, consider a small area at the surface of the water, which we will call A. Not to be confused with this A that just indicates that the air is there. Let's just remove this for clarity. Now, what force does this area experience both from the pressure from the air and from the pressure of the water? Because it's both in contact with the air and the water simultaneously. We know that the force due to the pressure of the water will be equal to the pressure in the water multiplied by this surface. And we know in the same fashion that the force that is experienced due to the pressure in the air is the pressure in the air multiplied by this surface again. And now here, of course, we see a problem arising if Pw, so the pressure in the water, and Pa, the pressure in the air, are different from each other. Since this surface is the same in both cases, this would imply that the force exerted by the water on this surface would be different from the force exerted by the air. For instance, if you thought that the pressure of the water would be larger than the pressure of the air right above it, that would mean that the force exerted by the water would be larger than the force exerted by the air. And this, in turn, would imply that there would be a net force acting on this area right here. And we know from Newton's second law that if there is a net force on a piece of surface, or on anything really, that there should be an acceleration in the direction of this force. However, this is not what we observe. If we just take a piece of area on the surface of any liquid, then it doesn't move at all. And this is one way to see why the pressure at both sides of the surface of a liquid, or the interface between the liquid and the air, has to be identical. So this is the case at the surface of our liquids in all 3 of our openings. But this triggers the question, what the pressure would be at the bottoms of the 3 openings. So at a specific depth h. You would think perhaps that the pressure at opening B and C, meaning these 2 points right here, would be larger than the pressure at opening A, because in both B and C there is much more fluid above this point that exerts a force downwards and thereby increasing the pressure at a lower level. However, to see why this is not the case, let's look at the formula for pressure, where we have that the pressure at some point in our liquid is equal to the atmospheric pressure, or the surrounding pressure, the pressure in the environment in which we are doing our experiments, plus the following. Rho, which is the density of our fluid that we're looking at, in this case the density of water, multiplied by G, which is the gravitational constant, multiplied by H, which is the depth at which we are measuring our pressure. And this formula reveals a couple of things. First of all, it shows that pressure is only present when we have gravitation. Since if there is no gravitation, there will be no gravitational constant. And thereby, if you have a blob of liquid in space just floating around, then there would be no pressure inside of it. Second, and more important for this exercise, is that the pressure inside of a liquid is only dependent on the height beneath the surface that you're looking at. And if we look at our setup right here, then we see that all of these points that we were considering are at an equal depth h below the surface of this liquid. And therefore it means that the pressure at each of these points will be exactly identical. Because we know that the atmospheric pressure is identical, it's just the environmental pressure, 1 atmosphere. We know that the rho, the density of the liquid, is identical because all of it is simply water. And we know that G is the same for all of these points because, well, evidently we're doing this experiment here on Earth. So the only variable will be H. And this means if we were to draw lines of equal pressure, then it would just be horizontal lines that are parallel to the surface of our liquid. And the surface of our liquid is basically the interface between the liquid and the air. And this, of course, also shows us a different way to approach this question 1, because at the surface, H will be equal to 0. And if H is equal to 0, then we see that the pressure in the water, just below the surface, is simply P0, which is the environmental pressure or the pressure of the air. With the principles of these conceptual questions in mind, let's go to the second exercise where we're going to look at how to replicate the difference in pressure between standing on the surface of the Earth and floating in space. At this point, we know that the environmental pressure that we experience here on Earth can be written as 1 atmosphere, or if we write it in the SI units of pressure, this would be 101,300 pascals, where Pascal is the unit of pressure named after the French mathematician. We can also convert this unit of Pascal to something that we are more familiar with, namely 1 Pascal is 1 Newton per squared meter. And from these units, we see that pressure can be seen as a force per unit of area. But more on that later on. Now we are also told that space is a vacuum. And what does this mean? Well, it basically means that the pressure in space is 0 atmosphere, or said differently, 0 Pascal. And because of this, many people say that if you are floating in space, that you would basically explode due to the presence of this vacuum, or well, the presence of a vacuum is basically the absence of pressure. And why would this be? Well, because your body is adapted to living under the pressure of 1 atmosphere, and therefore it simply cannot overcome the difference of 1 atmosphere. Or can it? Is there a way in which we can replicate this difference of 1 atmosphere in pressure on our bodies and see how our bodies actually react to this? Well, we know that if we go underwater, for example, if you go swimming in the sea, that we experience an increased pressure. Not only the pressure from the atmosphere, which we are all used to, but also the pressure of the water in which we are diving. Therefore, an interesting question would be, how deep would we have to dive in order to replicate the difference in pressure between the surface of the Earth and space? Or in other words, at what depth do we need to swim in order to experience a pressure of 2 atmosphere? Because if we know this, then we know that going from this depth to the surface again is experiencing the same pressure difference as going from the surface all the way up into space. So let's calculate how deep we actually need to go. So let's call the pressure that we are experiencing in the water Pw. We know from the general pressure formula that this will simply be equal to the pressure that is already all around us, so the atmospheric pressure that we experience at the surface, P0, plus rho times g times h. And rho is the density of the seawater, g is the gravitational constant, and h is the depth that we actually are swimming at. And we see, of course, that this is actually what we need, because we need to find h such that Pw is equal to 2 times P0, because we know that P0 is equal to 1 atmosphere, and so we need the pressure to be 2 atmospheres. Exactly 1 atmospheric pressure different with the surrounding pressure at the surface of the Earth. So we need to find this h. And not just any h, no, a specific h such that this Pw is equal to 2 times P0. So then we get our equation that 2P0 is equal to P0 plus rho times g times h. And at this point we can rearrange the terms in this equation. So we bring this P0 to the other side of the equality sign, which means that we have to subtract it from this 2 times P0. So we simply remain with P0, and then we divide away this rho times g. So we divide this by rho times g, and we already have our h. Let's now fill in these numbers right here in order to get our h. So what do we get? Well, in the enumerator, we have P0, which is simply 1 atmosphere or 101,300 pascals. In the denominator, we have first the density of seawater. And the density of seawater is 1,030 kilograms per cubic meter, which simply means that if we have 1 cubic meter of seawater, whatever form it may take, just as long as its volume is 1 cubic meter, then the mass of this volume would be 1,030 kilograms. And we multiply this, of course, with the gravitational constant, which is 9.81 meters per second squared. And this is the fraction that we need to calculate. And before we simply throw this into a calculator, I think it's very important to check the units, because the units will give us a check to see whether we made any mistake or not. We see that we're looking for a height, and therefore we need the units of meter. So let's see if we can get these units from these ones right here. We know that pascals are equal to newtons per squared meters. And in the denominator, what units do we have? Well, we have kilograms divided by meter cubed multiplied by meter per second squared. So this we need to be able to reduce to simply meters. And at this point, it might seem strange and even impossible, because we have a strange kilogram right here. How do we even get rid of this kilogram? Well, if we simply remember that F is equal to m times A, and we look at the units of this equation, then we have that Newton should be equal to kilograms times meters per second squared. Or if we switch this around, then we see that meters per second squared is actually equal to Newton per kilogram. And this is exactly what we can fill in right here. We can change this meter per second squared by what we found here, namely Newton per kilogram. And so let me now remove this trick right here, which is always handy to find the conversion between units, and let's see what we actually get. This Newton and this Newton can be cancelled out. And we see that now in the denominator, we can cancel out this kilogram. So what we are left with is simply meter cubed divided by meter squared, because this one becomes the denominator, and the denominator in the denominator becomes the numerator. Cancelling out powers of meter, we are simply left with meter. This is exactly the unit that we need because we're looking for a height. So the units are correct, so we are confident that we didn't make any mistakes. And at this point, we can simply throw this into a calculator. So we have 101,300 divided by 1030 multiplied by 9.81, and we already know that our units are meter. This comes out to be 10.025 meters. And of course, we need to remind ourselves what we actually calculated here. And to do this, let's go back to our sketch. We found that the depth at which we need to swim is approximately 10 meters. And at this depth, we are experiencing a pressure of 2 atmosphere. This also means that if we would be swimming at this depth and we would go to the surface again, we would experience the same decrease in pressure as we would going from the surface all the way into space. And it is in this way that you can replicate the difference in pressure that you would experience if you would be floating in space. Let's now go to the third and final exercise, where we're going to see how you can calculate the force on a surface at the interface between two different pressures. And as an example, we will calculate the force with which you would be sucked out of a spaceship if there would be a hole in it. First, the basic formula. The force that is exerted by a pressure difference on a specific surface is equal to this pressure difference, or simply this pressure, multiplied by the area of this surface. And this is a very basic formula which allows you to calculate a lot of interesting things. For example, the scenario where there would appear a hole inside of your spaceship while you're floating in space. Let's say that you're in space orbiting around the Earth in some futuristic tourist attraction. Because of course this is a tourist attraction, the spaceship needs to have windows in order to look out and awe at our pale blue dot. However, let's say that misfortune strikes and one of these windows is broken and is completely gone. Now, since of course the cabin of this spaceship is pressurized at 1 atmosphere, such that the same pressure as would be on the surface of the Earth, and space, as mentioned before, is at 0 atmosphere or a vacuum, there will be a large pressure difference between the inside and the outside of this cabin. And because of this, all of the air molecules inside of the pressure cabin are rushing out in order to diminish this difference in pressure. This rushing out, of course, brings with it a force. And it is this force that we will be calculating in order to see if there is anything that can be done about it. And in order to calculate this force, We need the pressure, which in this case is 1 atmosphere, and the area of our surface. In this case, that would be the area of a window. So let's see, we have pressure being equal to 1 atmosphere, or equal to 101,300 pascals. And then we need to find the area of a window. Let's say that the dimensions of the windows in this cabin are approximately the dimensions of a window in your typical airplane. Let's approximate it as being a circular window with a diameter of roughly 30 centimeters. This means a radius of 15 centimeters. And knowing this, we can easily calculate the area of such a window. We simply have r squared multiplied by pi, since it's a circular window. This is of course 0.15 meters squared multiplied by pi, which turns out to be 0.07 meters squared. And we have everything we need in order to calculate the force that is exerted on the area of this window at the interface between the cabin and outer space. We have F is equal to P multiplied by A, which is equal to 101,300 Newton per meter squared, because let's remind ourselves that 1 Pascal is equal to Newton per meter squared, so the force per unit of surface, multiplied by 0.07 meter squared. And we see here, of course, that the units check out very easily because we're left with Newton, which is, of course, the unit of force. Throwing this in a calculator, we find that this is equal to 7,091 newtons. Now, this might seem like a lot because it would be equivalent to roughly 700 kilograms here on Earth. However, it turns out that if you cover the surface of this window by a very thick book or a piece of wood of a considerable depth, then it would already be fixed. So if you find yourself in such a situation, or a much less extreme situation in an airline or airplane, then you can simply use common objects in order to cover the broken window and everything will be fine. But still, you would rather not have such a misfortune hit. And this brings us to the end of this first video in our series on hydrodynamics, and I hope that you're now more familiar with the concepts of pressure and its corresponding force. Again, if you have any questions, leave a comment in the comment section below, or of course join our new Discord server where you can freely interact with myself and fellow students. And with that, I thank you for watching and I will see you in the next one. Bye.